Okay. Well, sorry. So it's my pleasure to introduce the second speaker of this morning, José Pacifico from Universidade Federal do Rio de Janeiro. And she will talk about some old and new results on Lorenz attractor.
Thank you very much for the introduction. Okay, I will talk about this old and new Lorenz attractor, but indeed not. I will not cover everything for sure. And then let me see. Okay, and then the goal of this talk will be to give you an overview of Lorenz attractors, ending with the results with Yang and Jiagang, informally announced as the classical Lorenz attractor supports a unique measure of maximal entropy. And another theorem is that typically, this means that for an open set, Lorenz-like attractors of a flow on a t-dimensional manifold, compact manifold with d bigger or equal to 3, supports a unique measure of maximal entropy. Okay, and then to start, let me, no, I'm confused. Okay, old times. Of course, this is the old times from my point of view. I will not cover everything, just what I mean, and it's interesting to end with my results with Fan and Jiagang. And then Lorenz, we start that with the famous articles of Lorenz, where he put this equation here, just that is known as a Lorenz equations, he was trying to even we studied how to say this, the climate, how the evolution of the climate during a long-term evolution time. And the numerical simulations for this, for the chosen parameters, this means for A equal to 10 and R equal to 28 and B 830, there is a neighborhood such that for almost point in these neighborhoods, the orbit tends to a chaotic attractor. What is attractor? The attractor is a bounded division in the phase space invariant on the time evolution, to which the forward orbits of the most nearby points converge. And what makes an attractor chaotic is the sensitive with respect to initial data, which means that any 2 points, doesn't matter how nearby they are, during the time evolution, they will separate in the they will diverge. And the Lorenz conjecture was that the flow generated by the equations above contains a volume zero attractor that is sensitive with respect to initial data. And okay. One question is why the Lorenz attractor surprised the mathematician. You know that the paper by Lorenz was published in the beginning of the 60s. And the point is that at that time in the Berkeley school, led by Ismail, Ismail was laying the foundations for uniform hyperbolicity, which assumes that the tangent bundle to the flow is, how it is, okay. The tangent bundle, write as a direct sum of invariant by the derivative of the flow, such that the restriction to each of this flow, if you take the E, and the inverse of the flow restricted to F, they contract uniformly vectors. And the presence of an equilibrium accumulated by regular orbits prevents the Lorenz attractor from being hyperbolic. Thus, during the 60s, when research was focused to understand the hyperbolic system, Lorenz papers went completely unnoticed by the mathematical community. And the first, as far as I know, the first mention to Lorenz equations and the solution to the geometric Lorenz attractor was in the West by Guggenheim, that he, in a strange attractor published in the volume of bifurcation in 76. And in the East, it was by Aframovich, Bikov, and Shinnikov in 77. And the Guggenheim, indeed, he made the comment in this paper, is a strange attractor. The example is based upon numerical studies of a system of differential equations introduced by Lorenz. And the system studied by Lorenz seems to have the dynamical behavior of our example, but we do not attempt to make the estimates necessary to prove this statement. Okay? And you know that it took one decade in time just to the mathematician started to study the Lorenz paper, the Lorenz equation. By the way, the attractor generated by the real equation by Lorenz is nowadays referred as either a real attractor, Lorenz real attractor, or the classical Lorenz attractor, okay? And in the 70s, it appears a paper by Guggenheim and Williams in 79, and the name is Structural Stability of Lorenz Attractors, and where they established the main topological properties of the geometric Lorenz attractor. In particular, they showed that the geometric Lorenz attractor reproduces the behavior observed by Lorenz. Okay, and this is the skeleton for the geometric model. What they assume, they start with a flow here, defined on a neighborhood of the singularity, and the eigenvalues here. This is a linear flow, and the eigenvalues satisfies the same relations that for the Lorenz equations. In other words, you have three real eigenvalues, two contracting eigenvalues, one is stronger than the other one, and just one direction which is repelled. And then you just complete the flow like this, you push from this side. So here, this is a cross section, then you just push and through some movement, a composition of extension and the translations, and like this is like to push the orb, and you get this picture here, and because of the relation of the eigenvalues, you have that the half part of the cross section comes to a cusp triangle in each side, and then you push back to the cross section. You can do this in such a way that you have a preserved defoliation. I don't know what happened with my slide here because it's a little bit out of the goal. I don't know. The meaning is in this slide is that, okay, you have the main hypothesis for this model is the existence of a stable foliation in the cross section that's preserved by this operation that you do back to the cross section. And once you have this foliation, you can just project and you get a one-dimensional map like this one. What is the advantage of this? The advantage is that you start to study a flow in a three-dimensional manifold, and then you pass through a with the cross section, you have a two-dimensional system, and projecting to the interval, you have a one-dimensional map and one-dimensional flow. You prove all that you want for the one-dimensional map, and then it's possible to return it to the real flow in three-dimensional, just pushing back through this foliation. Okay. The main difficulty that you want, what was the, okay. In the 80s, after this seminal work by Guggenheim and Williams that appeared, indeed, we study more this paper than the paper by Tunikoff, Birkhoff, and Tunikoff, because there were that was the paper that we were studying, because at that time it was quite hard to get all the papers from the East, no, in the 70s. And in the 80s, after this seminar works, there was an explosion of articles around the Lorenz attractor. And the focus was split into several strands. One trying to prove that the flow generated by the Lorenz equations contained an attractor of zero volume, and another one trying to realize the Lorenz attractor through a given equation, another extracting the topological properties up to exhaustion. But while the discovery of the Lorenz attractor led to fundamental developments in dynamical systems, the Lorenz equations themselves continued to resist all the attempts to prove that they exhibit a sensitive attractor. And the real Lorenz, or the classical Lorenz, a successful approach for this kind of the real Lorenz attractor was through rigorous numerics. And there is the book by Sparrow, one of the first ones that appears at that time, that takes account of many of the results developing in the first years that people were looking at these equations. Later in the 90s, in this way, or numerically, it could be proved by Hastings, Troy, Miska, and Mrozek, that the Lorenz system of equations exhibits a suspended Ismail horseshoe. And this implies, in particular, the existence of infinitely many closed orbits. And the main difficult to prove this was, you cannot avoid that when you approach the singularity, the solutions slow down. And which means that unbounded return times and so unbounded integration errors. This was eventually solved by Tucker in the armored return of the center. And it consists of a beautiful union of computer assistant proof together with a nice normal formula satisfied for the flow in a neighborhood of the origin. And the main results continue. Bunimovich and Sinai, they have indicated a program that could prove that the Lorenz equations have a transitive attractor. And in the late 80s, Hellish and Robinson exhibited the first explicit examples, explicit equations of systems with strange attractors of Lorenz type. And one list of work on this kind of problems was to try to find the Hauser dimension of the geometric Lorenz attractor. And many authors have addressed this problem, calculating the Hauser dimensions for the geometric Lorenz attractor. Indeed, Steinberg gives the Hauser dimension in terms of the pressure, Abramovich and the passing, given the terms of the Lyapunov exponents and the entropy. And they also, they they got that the house of the dimensions is bigger or equal to 2. And Mora and Lizana, they proved it appears the first paper that the house of dimension is bigger than 2 in a very particular case, quite unstable case. Finally, with Gugu Moreira and Sergio Romana, we could prove that for typical geometric Lorenz attractors, the house of the dimension is strictly bigger than 2. And we could relate this with the interior of the Lagrangian as well of the Markov spectrum of typical geometrical Lorenz attractor is non-empty. And variants, you know that Grovella introduced what is called the contracted Lorenz attractor, that is just as much equal to the geometric Lorenz one, the original one. You just invert the relation between the eigenvalues, and you have this kind of attractor here. And this is the attractor, and this is the one-dimensional map that you can still, in this example, we still have an invariant foliation that you can project in the interval, and you get the one-dimensional map. Now is different from that one, that because it has it's not here is tangent and not the infinite. The tangent here, when you comes to the singularity from the right and from the left, it's 0 and not infinite like in the original one. And Bonatti, Marino, and Viana, they proved that Lorenz attractors exhibit Lorenz attractors with arbitrary expanding dimension. And with Barros, Diego Barros and Bonatti, we constructed what we call upper Lorenz attractor and down Lorenz attractor, and this means the cross section in this example that we construct is not a rectangle anymore, but a cylinder. And this is like what we call upper Lorenz attractor, and his is a down Lorenz attractor. And recently, Bonatti and Pinksky, they give an extension on a three-sphere of the geometric Lorenz model. And okay, now in the 90s with Morales and Pujals, we provide a characterization of the robust transitive attractors for three flows, which the Lorenz attractor is the more significant example. The theorem is robustly transitive attractors are partially hyperbolic invariant sets with volume expanding central direction. Moreover, robustly transitive attractors without any equilibria are hyperbolic. Okay. And after this, what happened after this work, we significant advances in the period were achieved through the work of many authors who gradually turned to the statistical and stochastic point of view of the Lorenz attractor, because in the beginning we were more interested in the topological properties of the Lorenz attractor, and during all these years we turned to the statistical and stochastic point of view. I highlighted the work by Lusato and Melbourne before, proving that the Lorenz attractor is mixing, and the work of Araújo and Melbourne, proving that the classical Lorenz attractor has exponential decay of correlations. Okay, and this is finally I am arriving to our result that I want to talk a little bit more, which was developed with Yang and Jiagang. And the theorem is that there exists an open dense subset in the C1 flows on a D manifold, compact manifold, such that every flow in this open and the set, and every sectional hyperbolic attractor lambda of x, and every holder continuous map phi from x to r, satisfying that the value of this function at the singularity is less than the pressure of phi related to along all the singularities, there exists a unique equilibrium state mu supported on lambda. Okay, I will explain the terms. And what is a sectional hyperbolic attractor? A sectional hyperbolic attractor is just if it admits a dominant splitting, which is one, the direct sum of ES plus, this is like a central one, FCU, invariant under the derivative of the flow, and the vectors in ES are uniformly contracted by the derivative, and is dominated, and the central unstable is sectional expanded. It means that any subspace, two-dimensional subspace contained in this space here is volume expanding. Okay, and what is a Lorenz attractor for us in any dimension, any with d-dimensional manifold is just a sectional hyperbolic attractor. Okay, this is the definition we adopted to a Lorenz attractor in higher dimensions. Okay, how will we prove the result? The structure of the proof is just we follow the idea by Bowen's method, which is the following: that expansiveness plus specification plus regularity on the observable, you have uniqueness of equilibrium states. This is an old series of papers for homeomorphism and after for diffeomorphism by Bowen in the 70s. Okay. Okay, and so let's go back to, I have to give some notions. For instance, for expansiveness now, first, let me define what we call infinity Bowen balls. This means that you have the flow generated by a vector field, and given some point in the manifold, we denote xt, stands for the orbit, the segment of orbit for s less or equal to t. Okay, and for t bigger than 0, the Bowen metric is just you define that 2 points is the super of the. Just take the orbit and look at the super of the distance between the point to point, no, for in this segment of orbit, and the epsilon Bowen ball is just you take if you fix a point x, here you have x is the set of points such that the distance of the Bowen metric, the Bowen distance between x and y is less than epsilon. Okay. Okay, and we say that this Bowen ball is degenerate at x if it's only the segment of orbits. You have the segment, the Bowen ball, you just take a ball and start iterate, and along a segment of orbit you are nearby. Okay. And expansiveness, how you define this? Expansive is that it's expansive if the Bowen ball is degenerate at every point. Okay, almost expansive if the set that you call such that the Bowen ball is degenerate at X has full measure for any ergodic invariant probability move. And H is expensive if the bowling ball has zero topological entropy for all X. And consequence of expansiveness is that, okay, if you have that it's expansive, it implies that it's almost expansive, which implies this is age expansive, which implies that the metric entropy is upper semi-continuous as a function of the measure. And this implies that the equilibrium states exist for all continuous map function phi. Okay. And back to the proof, what you do. There is existence. We are trying to prove our theorem that there is an open and dense set of flows such that for each attractor there, for under some conditions, you have a unique equilibrium state. Okay. First, you have to prove the existence. The existence is, the point is that, okay, if before all this work with Jiagang and Jiagang, we prove that if lambda is a sectional hyperbolic for the flow, then the restriction of the flow to the attractor or to the sectional hyperbolic is almost expansive. Then we have that the existence is guaranteed by what I said before. And to achieve specification and the regularity on the potential that was the to follow Bowen principle method, we extended the method developed by Klimenhagen and Thompson. What is this method? This says that, okay, if you take a flow in a compact metric space and a continuous potential, and you suppose under certain condition this set here is what is called the obstruction to expansiveness. The meaning is not defined here, but it's just the point that where the pressure restricted to the segments of the orbit is such that the Bowen ball is not trivial, has the pressure of the set is less than the pressure, the total pressure of the system. And if there is a decomposition like this for every M, such that there is one set GM has tail specification at scale delta, and phi, the potential, has the Bowen property at scale epsilon G, and the depression of some set restricted to the bed set. I would say that this decomposition you have G means for the good sets that I will define later, okay? And these are the extremum points of the orbit that I will explain, and then the flow admits a unique equilibrium state. Okay, this I will explain in the next slides, the meaning of these terms in this theorem, okay? And I will comment that the obstruction to use directly this criterion for the flow that we are considering is not possible just because of the item 1, because you will see what I mean. Let me just explain the terms. First, the composition means just that you take every segment of orbit, you split in 3 parts. This one is what we will call G, that's the good part, and you have the extremum here, and the points of the segment. Okay, in the beginning it's just this. And what the GM GM is the set of orbit segments that such that the initial part is less than or equal to m, and the end of the segment is less or equal to m. Okay, just like this. And then what you have specification. Specification, there are many meanings for the specification. It's just you follow the shadow by parts, the orbit, and you have some gap in between. Here we say that is weak specification at scale delta, because we let this gap between, when you follow the segment here, you have one segment here, another one. Then you follow you shadow the orbit in this segment, and then there is one time here that can be is less or equal to the gap. You can vary the gap is not fixed. And that's why they call weak specification. And it's scaling delta because you want to be, okay, smaller than delta. Anyhow, okay. And we say that one set contained in the space has weak specification if it has weak specification at every scale. Okay. And tail with specifications, just instead of you are worried about specification, just in the very long segments of your orbit. From one point, you take a segment of your orbit, you just want specification for t bigger than a fixed big number, okay, like this. And specification holds for, we say that a set has tail specification if there is a time, t0, so that all the segments with looking that for t bigger than t0 has weak specification at scale delta. Okay. And okay. The Boeing property. What is the Boeing property? It's just the regularity, what Boeing calls the regularity on the potential. If you take this, the potential, and you take this is like the big of sum, this, and it just you look to the super of the distance of along this segment, you compare the Boeing, the big of sum of the potential. Just compare, okay? And it's the Boeing property at this scale is that if there is a k such that the super of the difference along all points in the orbit for t of x, no, for t is this segment in the set, and for epsilon in the Boeing ball at x, this is less or equal to k. Okay. Okay. Then we had to improve the segment. Why this? Let me just what is the difference? Look, it's just the point there in the Klimenhaga-Thompson, why this doesn't hold for flows with singularities. Let me just is the item 1. Is for every m, GM has tail specification at scale delta. This means that, okay, no matter, you start with one segment, you look at the extremum, the part in the end of the segment, in the beginning of the segment. What you are doing when you vary m, you are just taking, you are increasing the good segment. Right? Just when you put m going to infinity, finally, you have to prove a specification almost to everyone, to the whole orbit. This you cannot prove for if this segment of the orbit approaches the singularity. That is the main difficulty. You cannot do this. So the improvement that we did in another work, we just fix this. Instead, we don't have to vary anymore. We were able to fix some set for an open set such that it has stay with specification, and all the other properties are the same. Okay, and this we can. It's just to get the improvement was the real motivation to apply this result for flows containing singularities approached by regular orbits. Because that one of the Klimen-Haga-Thompson, you cannot apply that item, okay? Okay, and then finally, what we have to prove to get our result is that a Lorenz attractor satisfies this kind of properties. And how you prove this? We have auxiliary theorems. The first one is just you have an open dense set such that you have the collection of orbits there has the specification, and then the other segment, the other theorem is that okay, in this you have another set that you have the Boeing property, and finally you get the intersection of these two the sets, and you get what you want. It's quite the naive. It's better to explain the naive idea of the proofs. Is that why the classical Lorenz has a unique, I'm calling it a measure of maximal entropy or equilibrium state. Let it just concentrate on maximum measure of entropy. We had proved before that given sectional hyperbolic attractor, a set invariant set of a flow, then there is a periodic orbit contained in this attractor. And there is we proved that any compact invariant sectional hyperbolic set, lambda, satisfying that the stable orbit of this periodic orbit is dense in lambda, and for any x in the attractor, the stable manifold of this point intersects transversally the unstable manifold of the periodic point, then this set has a unique measure of maximal entropy. Okay, and what happens is that it's possible to prove that the classical Lorenz attractor satisfies these two conditions here. Okay, and then we prove that the Lorenz attractor has a unique measure of maximal entropy. And what to do? Now, why the result is valid only for an open dense set? Because indeed, the Crevier and the Downway Jiagang, they proved that those equations, let me see, these two properties here only are valid for an open dense set of flows. Okay, and then this is the reason to get the result only for an open dense set of flows. Okay, and how to get the proof? The general, you see that you can prove that the classical Lorenz satisfies that two conditions there, and then it has a unique measure of maximum entropy. And now how to prove as we have to exhibit as much as possible of the good segments, satisfying the specification. There is the first theorem that I announced, and the Boeing property. Okay, and okay, so let's look at for flows without singularity. How we could prove this? We prove specification and the Bowen property reason with quasi-hyperbolic strings. What is strings is just a way shortcut to say that you have a segment of orbit, a finite segment of orbit with phi s of x for s between 0 and t, and the initial point is hyperbolic, yes, hyperbolic time, and the final point is FCO, hyperbolic time. And we can prove that the items 1 and 2 from above are satisfied. Why? Look, you have that just in our case, our splitting, you have the ES is hyperbolic, and then it's hyperbolic. We stay with any segment, it just go diminish along the time. And you have to take care of the central unstable direction that's not hyperbolic anymore, but it's just volume expanding. And then what you see, you try to find hyperbolic times means that F2 hyperbolic time is just when you go back in the CU direction, you get a hyperbolicity. Okay, and then you have that the periodic point, just the stable manifold of this periodic point cuts you start here in the neighborhood. You have cuts here in a scale delta, and then the unstable cuts the other one by the item 2. And this is like the lambda lemma. You just follow, you take the flow, and then in between you don't know, but then here you can approach the orbit segments using the classical estimates by the lambda lemma. And okay, and you can prove this just the specification property and also the Bowen property, because you have almost hyperbolicity here. Okay, in this case, without singularities, you are dealing with finite segments of orbits also. Okay. And now with singularities, what's the problem? In this case, we could, okay, we have the singularity, and then I just take one string such that the first point, the initial point, is far from the singularity, and then the ES is hyperbolic, and the end point of the string is outside the neighborhood of the singularity, and then you also could choose it such that this point would be a hyperbolic time. But okay, we could do this for specification, but for Bowen property, we cannot. Why? Because the Bowen property means that you have a better control along the orbit, along every point in the segment of the orbit. You have to have an estimative between the Birkhoff sum of the potential. Then, and when you are nearby the singularity, you lose the size, the uniform size of the central unstable direction. Okay. So we have to fight against the singularity just to get the Bowen property, no? And how we do this, how we win. We have to bypass this difficulty. We introduce another hyperbolic time that we call slow recurrence hyperbolic time. What does this mean? This means that I take it's possible to prove that you have a hyperbolic time for many it's like the Please lemma in hyperbolic time, such that when you can just take the string here, is a segment of orbit, and you just split it here. The red segment here means the time that this orbit passes through a neighborhood of the singularity. Okay, and what it's slow recurrent if the time that you spend outside the neighborhood is much bigger than the total time that you pass nearby the singularity here. During you take it, you can say that, okay, this segment of is a slow recurrency hyperbolic time for a good segment. If the segment can only spend a small portion of its time inside a neighborhood of the singularity. If during its last visit to this neighborhood, the orbit segment spends a time t, it must spend a bigger, much bigger amount of time outside. And this allows the hyperbolicity accumulated outside this neighborhood to overcome the lack of estimate inside it, and then get the Boeing property. And so we have from this point of view, we have to introduce not only hyperbolic time and the usual one, like from the Please lemma, but also this kind of recurrent hyperbolic time. And then you can prove the Boeing property. Okay, and the main tools used in the proof, the real proof, is that allows scale the linear Poincare flow and scale the tubular neighborhoods. This is a way to bypass and to try to make the brightest estimatives in a neighborhood of the singularity, and a fake local product structure formed by fake foliation, because you don't have invariant foliation. The splitting is not hyperbolic, but just dominated. And fake foliations near the singularities, and the transition between the foliations from the the foliation in the nearby the singularity to the fake foliation back and forth, and use slow recurrent hyperbolic times and central unstable recurrent times. Unfortunately, it's quite technical all that, but the naive ideas that I gave is just this. What you have to remember is that the singularity is really complicated to deal with, and then to deal with, to prove with the specification for you can just take the initial point in a segment of the orbit and the end point in the segment of the orbit far from the singularity, and then you have the result for specification. And if you want to prove the Boeing property, in other words, that the Birkhoff sum for the potential along the orbit, you have to introduce the recurrency, slow recurrency, hyperbolic times, and central unstable recurrent time. Okay, and okay, that is so. And this is just a propaganda of my book, because all the references are not here, of course, but you can find it's quite hard. There are many articles that I used to prepare this, but anyhow, in this book you have the many. I think it's like it's a 2010 book, so there are many other things that happen from there, but okay, still I like it, and that's it. Thank you very much.
Okay, questions?
You said you need an open dense subsumption for C1 singular hyperbolic attractor, right? And how about like just in dimension 3, if you assume like the singular hyperbolic attractor is robustly transitive or mixing, I think you can also get the thing, right?
Dimension 3.
Everything's
there's
okay.
no
Okay, just in higher dimensions.
problem.
Okay, you need it to be like a homology class for something like that.
Pass to some many details and what we do with not Lorenz like attractor, but class that more technical than this. I just try to do a resume.
Okay. All right. Thank you. Thank you.